Hi, this is Nalini Elkins with Industry Network Technology Council. Welcome to our webinar on segment routing in IPv6. Can somebody send me a quick note to let me know that you're hearing me okay, and that will be perfect. Great. I'm getting indications that the sound is okay. Please go ahead and send a note to me, a question or a message whenever if there's a problem with sound. And this session is being recorded so that everybody knows. So what are we doing here? This is a part of our focus on IPv6. We have a multi-year project, which you may have seen various webinars in that arena. We have been doing this, I believe this is our third year on IPv6 training and security and so on. So please talk to us. This is a collaboration between INTC and the India Internet Engineering Society in India. We have also received funding in the past from ISIF Asia, as well as ARIN. You may wish to, if you're wishing to deploy IPv6 in the APNIC area, you may wish to explore the IPv6 deployment grant. It can be quite generous in terms of how much that you get for deploying IPv6, and I encourage you to apply. So I'm just going to say just a couple of words about me. I'm the president of Industry Network Technology Council, which is a nonprofit, and I've have quite a few years in the industry and working with IPv6 for quite a few years. But let's talk about the interesting people who are the presenters. Yeah, you know, I'm hearing some whistling on the note. Okay, all right, fine. Yeah, no, thanks so much. Okay, so a few words about our first presenter, who is Dhruv Dodi. He is the immediate past president of the India Internet Engineering Society, and he is frankly one of the smartest and most competent people that I have ever met in my life. I've been working with him for at least very closely for at least 7 years, and he is just incredible. In this particular talk, he'll be giving an introduction and context for SRv6. He has many credentials. You can see many RFCs. He's filed for many patents, and as I say, you can read a great deal about him. He's an incredible guy. And then we're very lucky to have Darren Dukes, who will dive into SRv6. Darren is principal engineer at Cisco, and he works in routing and switching platforms, and he's currently focusing in depth on SRv6. And so I'm looking very much forward to having both Dhruv and Darren speak. Now let's go to Dhruv. So hang on 1 minute, and I will bring up his presentation. Okay. All right. So let's see.
Yes. Hi, Nalini. Can you confirm that you can hear me?
Yes, we hear you just fine. Thank you so much, Dhruv.
Thank you. So let me start. My job is to, as the title says, setting the scene, giving an introduction to segment routing, whereas Darren will do the heavy lifting and focusing on the key topic, which is segment routing on IPv6, or which is also called SRv6. Next slide. So what I'm going to do now is give a few words of basically why this whole concept of segment routing came into being. What is it offering to the world? Why people are talking about it? Well, the main aim is the ability for a node to specify the path that it want to take. So why this is new? Basically, let's compare to what happens in a normal case. In a normal case, you rely first on your IGPs, your OSPF and ISIs, which computes the shortest path using like the shortest path algorithm, and you always have the least cost path from any given node to any other given node. And what happens is when a packet arrives, which you look at the destination, and based on the destination, you decide which interface you need to send the packet out. So hop by hop, we make a decision in forwarding on who to forward based on the shortest path computed in the control plane. That's basically what has been happening in any normal IP routing. Now, what this leads to, basically everybody takes the shortest path, and there might be other paths available, there might be other requirements. Now if he took an example of what kind of requirements, maybe I need to find the least delay path. I don't care about the cost, but I need to meet a particular delay requirement, and thus I need the minimum delay path. Or I need to pick a set of links which have enough bandwidth, and they must be used because I have this particular traffic that needs to flow on this particular path. So I have multiple requirements, but I cannot rely on the usual shortest path. So I need a way to specify the path. And to do that specifying a path, there is a need for source routing, and not just looking at the destination address, but a way for us to put the route information at the source itself. And some of you may be wondering that isn't this something that has been that existed in the past? Well, yes, there was a routing header. It was deprecated, in fact, because there were some security holes in it, and now you don't see them in the network. So basically, this is not a brand new idea. This exists in the past. Now SR is coming back and maybe fixing a modern version of source routing in a way, and some of the requirements might still be the same. Now, another key thing was how to make this scalable and how to reduce the state that exists in the network itself. So there were ways to do, like, traffic engineering. There is RSVPT, there's MPLS-T, there is all the concept existed on how to do traffic engineering and picking up paths that I was talking about, but that leads to a lot of state in the network. So instead of maintaining state in the network, what if we put the information in the packet header itself? So that is the key idea behind the segment routing, that the state doesn't exist in the network, but it exists in the packet itself. The packet tells what path to take in the network. And of course, that will make things more scalable because the amount of state that you need to maintain in the network reduces significantly. And the main benefit here is how I can run my networks better, how I can add some agility, some flexibility, ability to do traffic engineering in a much more software-defined, intent-based mechanism. All the cool keywords that you might be hearing in the operation world. So basically, segment routing helps with that. And of course, increasing my resource utilization, doing more SDN-like operations, enhancing network operations, programmability, all that concept. So that's the main key for segment routing. Why segment routing? Now let's talk about what it is. So next slide, please. So this is basically, as I said, a modern variant of source routing. Again, no state in the transit router. Everything is in the packet header itself. And this packet header is created at the edge of the network, that is at the source node, which is also the ingress. So basically, we have an SR domain. That is a set of nodes that are participating in the segment routing based routing model. That is your SR domain. Your SR path, the path that we were talking about putting in the packet itself, is basically an ordered list of segments that will lead us from the source node to the destination node, the ingress to egress. And note the keyword, it's not an ordered list of nodes, it's not an ordered list of links, it's an ordered list of segments. So now the question is, what is a segment? Basically, an SR segment is an instruction that a node executes on an incoming packet. A very like a generic statement. And why it is a generic statement? Because we want to allow lot of type of segments and a lot of programmability with this segments. That's why a generic statement like instruction, and this instruction, a very simple instruction could be forward the packet on a very specific interface, or forward via the shortest path to a particular destination. And Darren will talk about in SRv6, in fact, we have a lot more segment types, and that's how you achieve programmability in the network. So it's a very generic concept, a mechanism for us to link a lot of segments, and these segments are identified by an identifier called a SID or a segment identifier. So when I take an example, I think these concepts will come to life. And of course, when Darren explains SRv6, you will be able to link these basic concepts. But throughout these presentations, you will hear these terms. So domain, path, segments, and SIDs. Next slide. So now basically there are, in the forwarding side, we have two data planes that are supported. You can do SR over MPLS. You can do SR over IPv6, which is called SRv6. In case of MPLS, and I'm sure you guys must be aware of the MPLS, MPLS allows a forwarding based on labels rather than on the destination IP addresses that we were talking about. So SR MPLS doesn't change anything. It basically says that SR segment can be represented in form of an MPLS label. And thus, you don't have to actually change anything in the MPLS header. Everything remains the same. And the whole segment list that we were talking about can be put as a label stack in the SR MPLS forwarding plane. And in case of SRv6, there we need to actually change something. We need to add a new extension header, a new routing extension header called SRh, and that will be covered by Darren, so I will not go in depth about that. But for both of these forwarding plane, you need to make changes in the control plane itself. And this control plane is common for both SR MPLS as well as SRv6. The concepts are the same, the set of protocols are the same, and in fact, the framework is the same. So what is the control plane? Well, control plane is the main brain of the whole operation. This is where we are distributing all this information, the SID information, so that the kind of forwarding that we want, the information that you are carrying in the packet, can be utilized in the is advertised to all the nodes so that they can act on the information that you are putting it in the packet header. So basically, your IGPs, your OSPF, ISIS, BGP, they need to distribute the SR information, basically called SIDs, to all the nodes in the SR domain. And of course, that's not enough. Sometimes you want to do some specialized path computation. You might be using a central controller, and that's where again the PCE comes into picture, and that's where one of my areas, and I chair the PC working group. And in fact, in the past, we have talked about PC in this set of webinars as well. So that's where PC comes into picture, and where the node can utilize the central controller and use the controller to do path computation, which is setting up the SR SIDs to meet the requirements for a particular set of path. And again, you have the SR policy framework, SR path framework, which basically allows us to do this job, meet the requirements by instantiating an ordered list of segments to meet a particular set of characteristics that we want for our traffic. And again, the set of protocols here would be like the use of BGP, use of PCEP, use of YANG to download this SR policy information at the head ends, so that when a particular set of traffic is put on this SR policy, that's where your SR path comes into play. Next slide. And next, what basically we need to do is just cover what are the different types of segments. So I'm covering two main types, and in fact, there are many other types, but the two mains one would be the same example that was taken earlier, that take the shortest path to a particular node. And this shortest path is actually ECMP aware. That means it's equicost multipath. So it's not just like one path, but if you are doing load balancing, it represents the ECMP aware shortest path to a particular prefix or a node. So in this example on your right, let's take the node which with the loopback address 555555, which has a SID 16055, and basically this SID is advertised via the control plane to all the nodes. And when in a packet you see the SID 16055, basically it indicates to the node that this particular packet is needs to be sent to 55.55, and it needs to be sent via the shortest path, ECMP aware shortest path to the particular node. And in case of an adjacency SID, basically you are identifying a local segment of a particular adjacency. And this basically identifies that not just the shortest path. I would like you to send this packet on a particular adjacency that I'm identifying myself. That is a particular interface on which I want you to send this packet out. So I will cover a few examples in the next slide, which should clear this thing up quite well. And just want to say that there are a lot more types of SIDs: Anycast SID, binding SID, egress peer engineering, which is where BGP AS things comes in. There are multiple types of other segments as well. So let's just cover a few figures, and then I will quickly hand off to Darren to cover the main crux of the presentation, which is SRv6. But let's just look at a few figures to understand the concepts that I just covered. So next slide, please. Basically, in this slide, you are seeing a node Z. It has a prefix SID of 100. As I said, that this has been distributed to all the nodes in the SR domain. And basically, at the case where the router A wants to send via the shortest path to the node Z, it basically needs to put the SID 100 in the packet. And this 100 is known to everyone along the path, that this is basically the shortest path, that I need to send this packet on the shortest path towards the node Z. And no other information about the path is put in the packet. We are not saying that on which interface that you need to send. That information is known at each local node itself. In case of a prefix or a node SID, that only information that is based on that you need to send the packet on the shortest path. And if something breaks, for instance, a particular link goes away, then of course your shortest path changes, and maybe the shortest path on top doesn't exist, and the yellow path on the bottom will become the shortest path. So again, nothing needs to change. Your SID would still be 100. It's just the path changes based on the local routing information within the SR domain. Next slide. And in case of an adjacency, basically here what we want is, okay, I don't want to rely on the shortest path. I have a very specific path, that is one that is identified in green here, and I would like my packet to follow this particular path itself. So what I need to do is I have to identify each of the adjacencies and stack them up, especially in an MPLS world. This is how the stacking of the adjacency SID would look. And basically the topmost level would tell me the most immediate information, that at node A, okay, 1002, that means I need to send the packet on this particular adjacency. And this information is popped out or removed. So again, now the top level is 2004, which basically means I need to send the packet on the link BD. The same thing happens, you pop 2004 and so forth. And at the end, you pop the last level and then send it to Z. So the whole information is put in the packet itself, adjacency by adjacency. So this is a strict path with all the links identified. But what can happen is you can have a mixed case as well. And that's the next slide, which is my last slide. In the mixed case, basically you can have both a node and node/prefix SID as well as adjacency SID together. So basically what I'm trying to say here is, oh, I would like the packet to go to the node Z, but make sure it goes through this particular link, the link between D and E, that it must go through this. So I have to identify this adjacency 4005, which is in the middle. And then I need to say, first you need to reach to the node D, which is identified by node SID 1001, then take the adjacency 4005, and then go send the packet towards the destination Z, which is identified by the prefix SID 100. So that information, I put it in the packet itself. So as the packet travels from A to B, the top mode instruction is 101, which means I need to still send it to D. At D, the topmost level is 101. Basically, I will pop out because that's me. And then what is the next instruction? Send it 4005, which tells me to send the packet on the link DE, and I pop the topmost label, and at E, basically I see the instruction is send the packet to Z, and that's what I do based on the shortest path information that I have of how to reach from E to Z. So this is basically an example of a mixed case in segment routing. So these concepts that I said are common for both SR MPLS and SRv6. Now, what Darren will do, will try to say that how do we achieve the things which are more intuitive in case of SR MPLS, because even in the segment routing world, the SR MPLS came first. There was demand to do that on an MPLS data plane first, actually because MPLS data plane didn't require much of changes. The push, pop, all these mechanisms were already existing in MPLS, and it was simply used in case of SR MPLS. Whereas in SRv6, there was a need for a new extension header, and that's what Darren will talk about. So maybe next slide, and then let's do the handover. And the focus basically is on SRv6. And now let's see how the concept of SR domain, SR path, node sets, adjacency set, and in fact, a lot more. So the key thing is SRv6 is in fact a much more enhanced version of segment routing, and it can do way more things than what SR MPLS can do. And off to Darren, and hope I set the stage nicely for you to take forward. Thank you. Thanks everyone for being here.
Oh, thanks so much, Dhruv. That was great. Very, very exciting. So I'm going to take it off now to Darren.
Great. Yeah, thanks, Dhruv. That was an excellent introduction. Hey, and before we get started, I see there's like maybe ability to people to raise hands here. If folks want to raise hands or find the button to press to do that, to tell me, are you working on enterprise networks? Raise your hand if you're working on an enterprise network. Maybe I'll be able to see that. And as I get going, as Dhruv said, this is Introduction to SRv6. I am going to focus on the data plane. And SRv6's data plane in particular, and I won't be covering everything. There's like Dhruv had mentioned, there's a lot of content to cover related to SRv6. You know, there's the whole control plane side of it. There's the ISIS, OSPF, BGP, BGPLS, and all that stuff. There's the PSEP size. There's SR policies. We could spend probably several hours talking and kind of giving tutorial on all that. So what I'll do is I'll focus on the SRv6 data plane, give an introduction to that. I'm going to cover some of the some things that Dhruv already had mentioned. Hopefully I won't hit too many of them, but we'll see how we go along here. So this is a bit of a detailed sort of splurge of the SRv6 specific standards that are making their way through the IETF right now. You can take a look at this later, but we've got a set of architecture documents. We have the SRv6 segment routing header, RFC8754, the network programming, 8986, and these are the two areas that I'm going to concentrate on today. We've got a number of use cases. We've got distribution of SIDs and ISIS and OSPF. We've got BGP link state, and we've got overlay services as more of a use case using BGP. We have OAM, and we have a whole bunch of performance measurement related activities going on for segment routing in general, and that are relatable to SRv6. So like I said, we're going to concentrate on the SR header, RFC8754, and network programming 8986, and give you guys an overview and some depth on those things. Okay, like Dhruv had mentioned, segment routing, source routing, scalable, simple, and where SRv6 comes into play here is that we really make this thing end to end, right? So in the MPLS world, of course, we're restricted to MPLS networks. IP and IPv6 is end to end. So the ability to expand that SRv6 and SR domain is pretty huge, and bring it closer to our endpoints is much more possible with IPv6 as our data plane than it was with MPLS. On the simplicity side for SRv6, really the intent to minimize protocols or eliminate protocols is strong. The protocol elimination that happens with SRv6, of course, is that we no longer need to use MPLS to get a whole bunch of cool traffic engineering and traffic steering features and source routing features. And Drew did mention the two data planes. I'll just say that the SRv6 data plane leverages RFC8200. Just need to move some of the content away here. Leverages RFC8200 to describe the routing header, and then it extends that with the SRH to say that a segment is an IPv6 address, so one segment is one IPv6 address for SRv6, as opposed to a segment being a label for SR MPLS. And a segment list is simply a list of addresses that are stored or placed in an SR header, and we'll get into what that SR header looks like. And like I said, IPv6 gives us reachability right across from client to data center, and that's the real thing that we want to build on. And why could we not do our SRv6 forwarding and traffic engineering with IPv4? Of course, IP reaches end to end as well. IPv4 does. There's a number of things that IPv4 just didn't do with limited address space, with no ability to provide engineered load balancing, with no native VPN, right? So we've got additional UDP headers, VXLAN, GRE, et cetera, on top of IPv4. Of course, it provides us some great VPN functionality, but nothing native in IP, of course. MPLS has native VPNs built into its MPLS labels. No traffic engineering to speak of on the MPLS side, we certainly did, and no service chaining, explicit service chaining without the NSH, or if folks are operating enterprise networks, you'll be using VLANs for service chaining all over the place as well. So with SRv6, we really want to move that simplicity back to the IP header, back to the OSI model, right? So we don't have too many additional protocols. In fact, we're trying to do everything with just IPv6, and we'll see what that unlocks. And what we're working on unlocking is the ability to do traffic engineering and high quality FRR, provide VPN services, network function virtualization, along with making this whole thing scalable. And so that was the intent behind this SRv6 data plane. And that SRv6 data plane started from a concept that that the network could really operate as a computer. This is different from the MPLS side. So if we have this source route, this source routed idea, and we want to be executing instructions at each step along, at multiple hops through our network, really that network could, you can conceptualize it as operating as a computer. It has a list of functions that are operating at locations, and those network instructions for SRv6 are described by 128-bit SRv6 SID. That's 128-bit IPv6 address, right? Those instructions have two portions to them. One is a locator portion, the other is a function portion, okay, just broadly speaking. The locator tells us how to reach the location where the function's executed, and the function tells us what to do when we get there. We can implement any possible function at that node, of course, depending on what the NPU or what a VM or container can execute at the node that instantiates that function. And we have flexibility in how big or small we're making these locators and functions in the IPv6 address space within that SID. There's a little tweak on this. If any of you guys are and ladies are programmers, you'll know functions take arguments. And so we have arguments that we can fit into that 128-bit SRv6 SID as well. And we'll get, I think further on in the presentation, we'll get a chance to see what those are like. So what does a network program look like? a network program is really a program that's built of a set of locators and functions, okay? And essentially a stack of them, like we saw with MPLS, a label stack, right? We have a stack of SRv6 SIDs with much broader functionality, and we can consider them essentially a program the network's going to execute for that packet that's flowing through it. So when the active segment is locator 1 and function 1, we execute the function at locator 1 or at node 1. When the active segment in this packet is pointing to locator 2 and function 2, we execute function 2 at node 2, and the same thing for the function 3 at node 3 or locator 3. So what does that look like in a packet header? Okay, how do we put these instructions into a packet header? In IPv6, we have an IPv6 header and we have extension headers that follow it. One of those extension headers is the routing header, and we find the segment routing header as a subtype of the routing header. The active segment is moved from the SR header into the destination address of an IPv6 packet as it progresses across the network. Okay, where we previously popped in MPLS and we're popping labels off, we're actually moving kind of like a program counter that's active segment across the set of SIDs so that they get executed when the packet reaches that locator at that node. So what does this look like in a little more detail in the SRv6 header? All right, so on the left, we've got our IPv6 header. We'll show our active segment. We'll show how we handle next instructions, and we'll show some global arguments. On the right, we have our IPv6 header, which you'll be familiar with, their standard RFC8754 header. And we have an extension header that follows it. That extension header has a next header, a header extension length, a routing type, and segments left. That extension header is a routing header. It's pointed to by our IPv6 header. And that extension header has a routing header type 4, identifying it as an SR header. Within that SR header, we have a last entry flags and tags field. The last entry just tells us where some optional TLV data is. The segments left is our index into the next instruction in the segment list. And our segment list is the thing that holds all of our instructions in that SR header. And we're going to go through an example of this a bit more. So the active segment, as we said, is stored in a destination address. So when a packet with this IPv6 and SR header and payload is traveling through an IPv6 network, the destination address tells us where our first function is located and tells us what the first function is. The segment list then contains that list of next segments, and you'll notice that actually the order is reversed. When you see these SR headers in sniffers, you'll see that the segment that's closest to the top of the header is the last segment, segment 3, and the segment that's furthest from the top of the header is the first segment to be executed. That's because the segment's left value is actually an index into the next instruction in the SRH. Okay, so the active segment's in the destination address. Segments left tells us what the next instruction is in the SRH. And as this packet traverses each of these locators in the network, that segment's left decrements, and we get closer to the to locator 3. Okay. Now there's a couple of global bits of information in the SR header in tags and TLV metadata. I don't think we're going to get into talking about the TLVs today. There is one TLV that's defined in RFC8754, and that is the HMAC TLV. That TLV can be used to have any node within an SR domain verify and validate the segments in the segment lists with a key to HMAC. Okay. There's other uses that are being proposed for the SRh TLV right now, but that's the one that we currently have in 8754. and it's the TLVs really for use for the segments that are getting executed in the segment list as basically global data for them to either store or retrieve information from. And then we have a tag field as well in the SR header that is used to group to just indicate a group of packets or a group of packets or a member of any type of identifier. One example would be for microsegmentation, where we need to do some classification based on some microsegment of the traffic within the payload. Okay. The SRh tags, segments left, and functions are really optimized for hardware processing. So you'll see the higher speed NPUs operate on those and not necessarily look at the TLV and metadata that follows the SRh. The TLV data is of much greater use for function virtualization or microservices that may implement functions along the path that this packet is going to take. So let's take a look at an example here. In the in RFC8754 and in the architecture specification, we define an SR domain as being the system where segment routing is enabled. Okay, so it's a for SRv6, it's a closed domain where SRv6 is enabled, and for traffic traversing that domain, we'll encapsulate the traffic traversing the domain. So the blue domain here is our SRv6 domain. We have SIDs allocated in that domain. For any traffic entering from the left, from the outside of this SR domain, it will be encapsulated for its traversal of the SR domain. What does that look like? We can carry anything at that domain edge, so it could be V4 or V6 or layer 2 frames, whatever. We encapsulate that in an outer IPv6 header, which may include the SRh for its segment list, and then forward that packet through the network. And as it gets processed by each one of those segments in the network really acts as the thing that's executing the set of instructions that the source node has applied, right? And executes that program that the source node has described for it. So in this case, this packet is going to take a cross connect from 2 to 3 and get delivered to node 5, where it's going to be decapsulated. Okay, and at the egress P, we decapsulate our egress node. We decapsulate the outer SRv6 IPv6 header plus SRh, and we're left with the inner payload without modification. And as Drew had mentioned, there's a whole set of different segment identifiers and behaviors that can be implemented within that SR domain. The two critical ones that I'm going to describe first are the end and end.x SID behaviors. But before I do that, there's some conventions I want to just draw your attention to. The first one is the IPv6 addresses are, in these examples, A:(K), where K is a node number. The SRv6 SIDs are assigned from a different address block, B00K, where K is a node number, followed by a function value, right? So this is, when we talk about locator function, B00K makes up the locator, and then we're followed by a function in the IPv6 address. So at node 2, we instantiate an NSID of B002:1, and that's just local to this node. The control plane can advertise this. It could be, we could be using some SDN system, but more than likely we're using ISIS or OSPF and extensions in ISIS and OSPF to advertise this SID and its end behavior to the other nodes in this network. Okay. We also advertise reachability for the locator B00K at node 2. The end behavior is pretty simple. The network is going to forward packets destined to this NSID on the shortest path, because the IGP is advertised B002 as a prefix that's reachable via 2. When the packet reaches nodes 2, it's going to update the destination address with the next SID in the SID list. Right? It's going to pull it from the SRh, as we'd seen previously. and then it's going to forward according to that updated destination address. And that's all that this NSID's behavior does. We have an n.xsid defined in RFC8986 as well that does very much the same thing until the packet reaches the node. So we define this n.xsid B002:C4. It's also advertised by our IGP and distributed through the network so that a source node knows that it's available and compute a path using that SID. In this case, the SID function value C4, I use here to make it kind of obvious we're cross-connecting to node 4. It could be any value. It doesn't need to be C4. It could be anything. But locally, that value C4 or whatever else it is associated with the NSID, n.xsid, that is going to update the destination address when it's processed with the next SID in the segment list, and then it's going to forward via the associated interface for C4. Right. So this is the adjacency SID and MPLS. It's formally defined as an n.xsid for SRv6. So when that segment list is pushed onto a packet, it would first be segment, for example, here we've got segment B041. So this is an NSID at 4, a B005C6, which is an n.x SID at node 5, and then A8, which is just a destination node at address, the address for node 8. Those three things are placed in the segment list of the outer IPv6 header. And when a packet is forwarded with that SID list, it's going to go from 1 and take the shortest path to 4, where we're going to perform the end operation, go to the next SID, which is B005C6. At node 5, we're going to place A8 in the destination address of that packet and forward that packet on the adjacency toward node 6. At that point, A8 will be in the destination address, and we're going to take the shortest path, whatever it is, to node 8. And it's just regular IPv6 forwarding at that point. Let's take a look at some use cases. And for those, I'm going to introduce another behavior, end.dt46. Okay, so we've got our end behavior, end.x. Now I'm giving a third one, end.dt46. So this SID, B002V9, and of course V9 isn't an address that you'll ever see because it's not a hex. I'm using it just as an identifier. It could be any value for that function. V9 simply to say that this is an n.dt46 SID associated with VRF9. Okay, so what do we do when we receive a packet destined to that SID? Again, it follows the shortest path to the endpoint. The nomenclature for this n.dt is D says it's decapsulating. So we're going to decapsulate the outer IPv6 header, and we're going to forward that packet to a new destination via a VRF, right? And in this case, VRF9. And we're going to use either the v4 or v6 table associated with the VRF, depending on what the next header is in the IPv6 extension header list. If you remember, we have an IPv6 header, we have an SRh, potentially as our next header, and then we have whatever the payload is. In this case, the payload would be a v4 or v6, v4 or v6 next header type. And there are many other SID types. Oops, I'll go back here. We covered 4.1 and 4.2 n.x. This is from 8986. I just mentioned 4.8 n.tt46. We also have on the VPN side, because really these decapsulate and forward via a table or a cross connect, provide us the basis of L3 VPN functionality, forwarding via a table or via a CE. And we have n.dt or DX2s and n.dt2Us that provide us the basis of our layer 2 VPN forwarding capabilities for VPWS, VPLS. And there you can read what they do. They all decapsulate, and then they forward either, for example, via a particular v4 table, via an L2 cross connect, via L2 a VLAN L2 table lookup for a specific table, unicast MAC L2 table lookup, or decaps and flood, right? We have a couple other SID types here. N.B6 is an interesting one. So this is a binding SID that's bound to an SRv6 policy with encapsulation. So bound to another SRv6 encapsulation. So when we instantiate these SIDs in our network, we bind them to an SRv6 policy with a SID list, and the packet would then take that path to wherever its next segment is. NCAPS reduced is a description of B6 with NCAPS reduced is just an encapsulation with that binding SID that reduces the segments in the segment list a little bit. We have a binding to an MPLS SR policy. This allows us to cross SRv6 domains or SR MPLS domains from SRv6 domains. And we have a few flavors that I'm not going to get into too much, but they are modifiers of these behaviors up here. And these are all local behaviors to a node that are not, that are simply implemented and instantiated at that node. No other node within the network forwarding any of these SID types needs to know what they are. They just need to know the locator on which that SID's instantiated, just like we saw with the n.x SID. Okay, let's take a look. We're going to use that DT46 SID now that we learned about to provide a VPN service. So this is just an overlay VPN service for 10.08, and this service we're providing is using B04 V9 to forward anything destined to 10.0/8 to a VRF at node 4. Okay. With this SRv6 encapsulated packet, we'd be traversing whatever the shortest path is to node 4 before we decapsulate and forward within that VRF 9. Okay. But I want to use this example to show something else that gets built within the network, and that's a TLFA failure path. So each node will compute what. Let me describe this. I won't go into too many details on TLFA. We could probably spend a whole presentation on it. But much like IPFRR, we compute a post-convergence path, or for when there's local failures, and TLFA will actually compute that path with a segment list to make sure that that we will be forced to take that post-convergent path regardless of any of the intermediate nodes converging later than the node that detects the failure. So for example, node 2 computes a post-convergent path for a primary path via node 3 that's going to push an SRv6 header that includes the SID B06C5. So that's the cross connect from 6 to 5 that's instantiated at node 6. Okay, so when we're forwarding traffic to B04 V9 and we hit node 2 and our primary path goes down, we're going to forward that over the encapsulation to B06C5. B06C5 is going to get implemented at node 6 to tell that packet to take its high metric link, no matter what, take that link to node 5, and then we're going to forward that packet onto node 4. So this way we can, for any topology, we can compute a repair path that we know is going to get utilized on failure. Okay. This also lets us avoid the micro loop problem that's a little easier to show this way. When we get a failure at a point here and we take a repair path, usually we'd have to wait for convergence of all these nodes along the path, and we'd be looping packets back until all the nodes along the repair path have converged. Right? So if 2 just forwarded towards 6, 6 would forward back toward 2, and we'd loop there until 6 realized, oh, actually the shortest path is now via 5, and the same thing at 5. But what we do by computing the repair path with a explicit SID list is we can avoid those micro loops altogether. Okay, so we've seen that VPN case introduced. We've seen TILFA introduced using those two SIDs in an SRv6 extension header. Let's take a look at just a VPN service over a best effort slice, okay, which is essentially what we saw previously. B03V9 this time provides us a SID at 3 that implements this function to forward via VRF. And I don't think I mentioned it, but of course, B03V9 would be advertised from an egress PE to an ingress PE, where we'd instantiate the encapsulation over B03V9. BGP is one way to do that. There are other, SDN technologies that could be used for that as well to learn and then push that B03V9 at ingress PE. But as far as the base SRv6 forwarding is concerned, we don't really need to worry about how the control plane works at this point. So let's see. We have this VPN service, and we're assuming an encapsulation at node 1, where we're encapsulating with this SID B03V9. And the B locator block, that's the whole B block, gets associated with an ISIS base algorithm. Okay, so there's a concept in ISIS and OSPF flex algo that allows us to create multiple algorithms, and we associate a locator block with each one of those algorithms. Okay, so for SRv6, in this case, we've associated B with the lowest cost, best effort path. So that's the path that the packet's going to take when it traverses 1 to 3. Normally, if we're still using that B locator block, and we want to take a path that is not the shortest path, best effort, perhaps there's some poor delay on the link from 2 to 3 and 6 to 5, we'd have to push a segment list onto this packet of B02C5, which says first go to node 2 and then cross connect to 5. And then from 5, go to B03V9, right? So we'd have 2 SIDs pushed onto this packet, and then one in the SRH and destination address. But we don't really need to do that if we implement a new algorithm in our IGP flex algo that uses a new locator block that's associated with it, right? So node 3 would then advertise 2 SIDs of 03V9, one with block B, which is for the shortest path, and one with block D, which is the lowest delay algo. And the IGP would compute these topologies based on for this algorithm, the delay that's observed on its links. Okay, so we have the ability to compute multiple topologies in the IGP, and then associate locators and advertise locators in those topologies to ensure that traffic from 1 to 3 uses a particular topology when it traverses this network. Okay, and we can do that with only a single SID, just D03V9, to say decapsulate this packet and forward in VRF9 at node 3. Equally, we can add in network function virtualization. So remember previously I was saying, we've got a set of types of SIDs. Those are the ones that are standardized in RFC8986. You can take something like Snort, which supports SRv6 today, and instantiate a SID in Snort that says, when you send packets to this SID, perform your IPS on that traffic, and then forward to the next SID in the segment list. So we could build a network program of D02, whatever the Snort SID is, maybe it's 100, maybe it's 30, and then have the next SID in the segment list of that packet be D03V9, right? So we can implement a network function in our network just by adding it into our segment list, okay, without any VLANs or anything like that. And we can also, have it go over a particular algorithm to make sure it receives a certain treatment as it's getting that function executed. In this case, we've got two SIDs. We've got the snort SID and we've got the VPN SID that's pushed onto the packet. Just checking how I'm doing for time. Okay, I'm getting low on time. We have another EVPN VPWS example. I just want to touch on load balancing since we're getting close to the end of my time slot. Load balancing for SRv6 is best done via the flow label. You use a 3-tuple hash of source, destination, and flow label. We don't need to be jumping into the packet to look at next headers, as long as the source node sets the flow label based on a hash of its inner payload. Okay, and flow label based hashing is probably exactly as you guys would and everyone would expect. We hash and select a ECMP path or UCMP path based on our hash of flow label plus source destination address. That's the recommended hash. Of course, there's nothing stopping an implementation from looking further into the packet, but once the flow label is set, there's really no need. The last topic I wanted to touch on, and just a quick time check, we've only got a few minutes left. I can quickly go into this, or we can go over. What do we think, webinar managers?
No, I think let's. How much more do you have? Because I think I'm fine to go over. Yeah.
Okay. This is the last section.
Okay. Perfect. Yep. Okay.
So we'll move quickly through this. 5, maybe 10 minutes we'll go over. Okay, so you may have noticed in those previous examples and looking at the SRH that every segment adds 128 bits, right? That's 8 bytes. I remember back in, I don't know, 1990s when I was looking at IPv6 and realized that, oh, it's not 8 bytes long, it's like 16 bytes long. It was big, right? So each of those IPv6 addresses adds 16 bytes, and generally with SRv6 and with SR MPLS, our label stacks tend to be pretty small. But as Drew had mentioned, if you have an explicit path that you have to represent through a network via adjacency SIDs, your path can get relatively long, right? Not necessarily tens of SIDs long, but long enough that those 16 bytes are going to be feeling expensive to your MTU. So the Spring Working Group spent a lot of time working on compression of SRv6 SIDs, and it's come up with a draft that I think is pretty elegant in how this is done. IETF Spring SRv6 SRH compression. This is just a look at what's coming out and what's getting implemented out there, what's getting tested. Describes 2 flavors of SIDs, and those flavors get applied to the N SID and the N.X SID. 2 flavors of SIDs that allow for them to be compressed. So in these 2 flavors of compressed SIDs, we still have a program, we still have a list of instructions contained in a destination and SRH. We still have SRv6 instructions, which are the SIDs. We have an idea of a CSID container, which is just an SRv6 SID that contains a list of CSIDs. Okay, and CSIDs are, in fact, just the locator node and function bits of a SID. So if you remember all that block, that B00 or D00, it's all common stuff. And after the function, well, our functions don't need to be 64 bits long or relatively short. Right, it's after the function, there's nothing there. So the CSID is just that kind of essence of the SID that we can then compress. And I'm going to show an example with next, just because it's easy for me to show in a destination address. And I'm going to give you a description of how replace works once we see how next works. So we have 2 sites, site A and site B, and we have some VPN between site A and B. And we need to send traffic from site A, node 1, first to node 8, then to node 7, then to node 2 to meet whatever traffic engineering or service function chaining solution we're trying to implement. Okay, and we want to do this with a minimal number of SIDs. Normally this would be a 3 SID operation. We'd have an SRH with 3 SIDs. With this next CSID container, we can do that with just a destination address. And how do we do that? Well, there it is. It's some block BBBB here, followed by a bunch of SIDs that are all grouped together in a single IPv6 address. And you may be thinking, well, that's different than what you told me before. And yeah, it does look a bit different, but what we actually have here is a SID with a set of arguments. Okay. So we have our locator block, we have a locator, we have a function, right? And that 0800, and then we have some arguments to that thing. And let's see how we process that and how we advertise that. So ISIS advertises the SIDs for each of the nodes, as it usually does. In this case, it advertises them as reachable, and they're routable, but it also advertises the SID behavior. So B8 would be associated with an N SID with next flavor, and 7 would be associated with an N SID with next flavor, and 2 would be associated with an N SID with next flavor. And we do that for all the nodes in this network, but we're only showing the 3 we're interested in. And so when we've encoded those SIDs as a single IPv6 address, the next flavor gets executed at each of those nodes, and I'll show you what that looks like. So first, we forward this packet with the destination address of B872FTT4. And you'll remember we'd advertise B8 as reachable via node 8 and IGP. So simply traffic is attracted toward node 8 and forwarded just like all other IPv6 traffic is. At node 8, we copy the arguments. At node 8, that's where we've instantiated this function B8. Okay, so our fib longest prefix match matches a SRv6 function. We then execute the instruction, the behavior of that function at that node. And these next flavor SIDs say to copy the arguments into the active segment in the destination address. And essentially it looks like a shift of 16 bits in this case. And then fill the remaining bits on the right with 0, right? So we shift over to the next SID in the segment list. And the segment list in this case is contained entirely within this IPv6 packet, IPv6 destination address. So at this point, we've got B07 to FTT4, whatever left, and we're going to forward that packet on the shortest path to node 7 because that's what was advertised. Again, we do the same sort of function. We shift. The next SID that's in the list is B2 with its arguments of FTT4. We forward that because that's the locator for node 2. We forward that along, the path toward node 2. And it simply follows the shortest path till we get to 2. And at 2, we hit the longest prefix match on B02FTT4. Right? This is our end.dt4 SID that we had seen previously. So we know we're just going to decapsulate and forward the inner packet on the shortest path toward its destination via some VPN or some table at node 2. Okay, so we saw how at 1 the inner packet gets encapsulated with an outer IPv6 header with this interesting looking destination address that's been computed to represent the segment list 872FTT4. Okay, and then we do classic IP forwarding to node 8, where the next behavior, it's actually the next end behavior, tells us to copy the args and forward it to 7, and then at 7, copy the args, forward to 2. We do classic IP forwarding until we get to node 2 and decapsulate. Okay, that's how we compress, or one of the ways to compress SRv6 SIDs that's in Spring Working Group right now. There's another way that works particularly well for longer SIDs. These are 16-bit identifiers. The other way that works in the replace flavor that's documented in that draft keeps the same idea of these CSIDs, but keeps them stored in the segment entries in the segment list and doesn't replicate the outer block. Okay, so in that case, we always need the in that case, we always need the SRH, and we're going to be moving these CSID segments from the SRH into the destination address. And you can take a look at that draft. We're getting close on time here, so that is the last bit that I wanted to show you around SRv6. So we've covered the standards, we covered network programming and RFC8754, the SRH. We've covered RFC89E6 behaviors, and there are quite a number of them, and there are more getting standardized. These are local behaviors at a node that get advertised via IGPs. And we covered some use cases of TILFA, any sort of VPN, L2, L3 VPN. And we covered working group drafts on compression that says how we can compress some of those longer SRv6 segment lists. Okay, yeah, if you've got any questions, oops, that wasn't supposed to be there, sorry about that. If you have any questions, there's some links here. There's all sorts of stuff you can of course Google online as well. These are just some of the ones that I'm familiar with. If folks have questions, I don't see the poll up right now. Let me open that up. Yeah, if folks have questions, no, I could answer them.
So Darren, there's
what do we think?
Yes, sir. I know I'm running a little short on time myself, so let's just do one question. This is a great presentation from both you and Drew. Let me just ask a quick one. In terms of deployment, presumably most of the deployments are still MPLS rather than IPv6, or what have you thought?
Yeah. Yeah, absolutely. I mean, that is the incumbent technology. It's deployed everywhere, right? And that is known as service providers and others. At least I talk about the ones that are public. I mean, that we know of as service providers migrate to IPv6 only and simplify. Then that's when they look at the transition that we've seen, that I've seen anyway, to SRv6. But if they're running happily on V4 and MPLS, then that's where they'll stay until whatever point they decide to move on and add more services.
Perfect. Yeah. Thank you. Thank you so much to both of you, and to everyone else. We will thank you so much for attending, and we will make the foils, slides, and the recording available to you after the fact. So thanks again, everybody. Bye bye.
Thanks everyone. Bye bye. Take care.
Bye.